This is the final project demonstration for Curtis and Mauricio. Our final project is a remote control vehicle that is controlled over infrared light with user controls with buttons and variable speed selection through this potentiometer here, and the speed selection will be shown through these LEDs here. This will also have an ultrasonic sensor to determine the distance away from a wall, and it uses PWM to control motors. This is not implemented here in this demonstration. This will be discussed in the final lab report. So to control the speed, we will be adjusting this potentiometer here. And as you see, I'm going to set it to full speed, and that shows the red, yellow, and green LED turning on. Red showing that it's the slowest, yellow illuminating when the medium speed is picked, and green showing when the highest speed is picked. So now to finalize our selection, I will hit this button here, and the LEDs will turn off to show that our selection was made. Now that our speed has been selected, we will move on to the distance sensing. So as this car is remotely controlled through infrared signals, the user will be informed through sound with the speaker here, and the distance will be sensed with the ultrasonic sensor. So as the car gets close to a wall, the speaker can play a higher pitched sound to let the user know to stop the vehicle and even reverse the vehicle. So I will do the demonstration here. The range that the sound will play in is anywhere from 15 inches away down to 0 inches away. And I will demonstrate an object moving closer with my hand. So as I put my hand out in front of it, as I move closer, every 3 inches, the sound increases by a set frequency, and this will allow the user to know as you move closer to a wall. Next, what will be discussed is the infrared sensing system. So the clear LED is the infrared LED, and the black diode is an infrared receiving diode. So the sending signal is controlled through the pressing of these buttons here, and each button will send a different signal, either 10 microseconds, 30 microseconds, 50 microseconds, or 70 microseconds. And what is sent and received will be shown on the terminal. So first I will press this button here, and it sends a signal on the initial press and the release of the button. And here I will explain the output of this terminal. So here we see it pressed, it did the interrupt on the press and the release. We indicate that we did backwards direction. That's just the button that we assigned to that. And here the signal sent happened to be 322 tenths of a microsecond, which is 32.2 microseconds. And the signal that we received, this is the signal, that happened to be the same 322. So now let me press another button. Oops. Here. So as you notice, it only interrupted once, which is why we have the press and release triggering an interrupt, just to ensure that the signal will be sent. And we see that the signal was 523 tenths of a microsecond, and this signal was also received with the infrared LED, or the infrared receiver. So now to show that this system is actually working and not hardwired, I will position this receiver upwards and the sender also upwards. And now the signal is not going to be able to be sent. And I will now press the button again, just a couple times. And as you see, we have errors where it just says that the button pressed was backwards, but no signal was actually received. And so this shows that the infrared signal is actually being sent across that bridge. It should be noted that for this project, we have a body of a vehicle along with 4 DC motors that would be controlled through PWM. The code that is written to control the PWM has been verified to work. However, the DC motors would not respond to a change of duty cycle. The motor would either be full speed going forward or it would be off for whatever reason, no matter how much we changed the duty cycle of the PWM. This speed did not change, and the things that we tried, along with a detailed description, will be in the final project report. Thank you. This is an overview of the code written for our final project for Curtis and Mauricio. So first, let's take a look at the main function. The main function starts out with the initialization of the timer, the initialization of the GPIO, and the configuration of the ADC. So let's take a look at the initialization of the timer. The initialization of the timer includes the initialization of timer 6 and timer 7. Timer 6 is set to overflow and interrupt on that overflow at approximately 1/10 of a microsecond, and timer 7 is set to overflow and interrupt at 0.13 microseconds. Now let's take a look at the initialization of the GPIO. So all the clocks of the GPIOs used, C, J, and F, are enabled. And I won't go through the configuration of all of the individual peripherals. However, the ultrasonic sensor trigger, the LEDs, including the infrared LED, and the speaker pins are all initialized to be outputs. And the pins for the buttons, the ultrasonic sensor echo, and the infrared diode are all initialized to be in the interrupt mode for rising or interrupt mode rising and falling. The buttons are initialized to be in interrupt mode rising, and then the ultrasonic echo and the infrared diode are set to be in rising and falling, so we will be able to measure the time of those signals. Now let's take a look at the ADC configuration. So the clock is enabled for the ADC, and the main thing to focus on is that the ADC resolution is set to 12 bits, and we're doing it in single mode, single channel, and here it is configured. And then down here, this is the GPIO initialization for the analog mode of pin A6. This is so that we can read analog voltages off of this pin for the potentiometer speed control, which I will talk about coming up right now. So in the main function, we start off with an infinite while loop where we start the ADC and give it a slight delay. Then we pull for the conversion of this measurement. Then when the measurement is ready, we set the variable input to the ADC value, and Vin is set to this equation here. I'm using 33 instead of 3.3 volts as the reference so that decimals are not used. And here the 12-bit is used in that equation if we were to do an 8-bit resolution, 8 would be put in here. And so now we check to see if the voltage in is less than 0.6 volts, less than 1.8 volts, or greater than those. And if the voltage is less than 0.6 volts, we turn on the red LED and set the speed equal to 1. If it's less than 1.8 volts, the red and the yellow LED are turned on and speed is set to 2. And lastly, if it's greater than those voltages, all the LEDs are turned on and the speed is set to 3. So now, then we check to see if the ADC flag is 1. This is set to 1 when the interrupt for the ADC stop button is pressed. And this will turn all of the LEDs off. And if the speed is 1, we're going to set the threshold to 200. If the speed is 2, we'll set the threshold for the PWM to 128. And we'll set the threshold to 64 if the speed is set to 3. So something to note here is that the lower the threshold means the higher the duty cycle. So after that is done, we break from this loop. Now in the second loop, this is where we're going to be incrementing the time. So the time flag, if it is equal to 1, that means that timer 6 has overflowed, and that is happening every 10th of a microsecond. So we add 1 to time to keep track of it. Now every 10th of a second, we're going to start the ultrasonic sensor trigger. So this is going to put that pin high. And if it's every 10th of a second plus 10 microseconds, we're going to turn off that pin, and that completes the start of the measurement. And then we're going to also check to see if the distance is less than 15 inches. If so, we're going to toggle a GPIO pin for the speaker to be a certain frequency. Here, all this equation is doing is we are changing the frequency of the speaker between 10,000 hertz and 5,000 hertz, depending on the distance away. And it does these steps for every 3 inches. So 14 inches to 12 inches away, we're going to play a sound of 5,000 hertz. And then from 0 to 2 inches away, we're going to play a sound of 10,000 hertz. This will alert the user to steer the vehicle away from the object. As it is getting closer, the pitch increases to let the user know. Then down here, outside of that if statement with the time, we're going to see if the measurement is complete for our distance measurement. This is when the interrupt of the falling signal for the echo pin of the ultrasonic sensor goes down, and then we'll clear that flag and set the distance equal to this equation. This is the equation to convert the time of the pulse to the distance away from an object that the ultrasonic sensor is. Then here is the code for the transceiver. So here these 4 statements check to see if the left, right, drive, or reverse signals are being sent. And then it also checks to see if the current time is greater than the time end of that signal. So the infrared LED is being set to high on the interrupt of those buttons, and we're calculating the end time of those signals. And then here, if the current time is greater than the end time, we're going to turn off the infrared LED. Now for the receiver, since the left, right, forwards, and backwards signals are different pulse lengths, we're going to check to see what signal we received. So the left signal is approximately 10 microseconds. The right signal is approximately 30 microseconds. Forwards is approximately 50 microseconds, and backwards is approximately 700 microseconds. And we check to see if the signal is around this range, And if so, we share what that signal is, and we also, it is commented out here, but in the full implementation of our code, we would turn on a GPIO pin to set the transistors for the certain motors that are going to be turned on with the PWM. Those pins will be set to high to control which motors will be turning on and what polarization. This is not implemented in our code right now because of difficulties with getting the DC motors to run properly. A description of this will be in our final project report. Then down here, lastly, we have the PWM code. So if the PWM time, which is incremented every time the timer 7 interrupts, if that is greater than the threshold, we are going to set the GPIO pin to 1 and otherwise set that GPIO pin to 0. Thank you.